In the last lecture, we just started Lebesgue integration theory. To begin with, we shall quickly recall the main points in the last lecture. Please recall that in the Riemann integration theory, what we do is, given a bounded function, we shall approximate the function by a piecewise constant function or a step function, and instead of integrating the given function, we integrate the step function. The integration of step function will turn out to be approximation for integration of the given function, and we shall make this approximation better and better. Essentially, we deal with step function, piecewise constant function. When you want to generalize this into Lebesgue integration theory, instead of step functions, piecewise constant function, we deal with so-called simple functions. That's what our starting point, simple function. If you recall, a simple function is a measurable function, let us say from R to R, such that it takes only finite number of distinct values. Right? Phi is a function from R to R, phi measurable, and phi takes only a finite number of values. The range set is finite. Then we went for a representation of phi. Mainly we dealt with the so-called standard representation or canonical representation. If phi takes distinct values, let us say alpha 1, alpha 2, and so on alpha n, then phi has a nice representation as a linear combination of characteristic function. And that representation is summation I is equal to 1 to n alpha I characteristic function on ei, where the indicator function or characteristic function is defined on set ei, defined as follows. Ei is equal to collection of all x such that phi of x is equal to alpha I. And this representation we named as canonical representation. So this is a fundamental definition we need to start our integration theorem. Now, mimicking what we did for piecewise constant function or a step function in the Riemann integration theory, we can define integral for simple functions. So that was the next thing what we did. If phi is a non-negative simple function. Simple functions are measurable by our definition. Simple function with, let us say, the following canonical representation. Phi equal to summation I is equal to 1 to n alpha I chi ei. Then we define its integral as follows. Then we define. Can you pronounce, just for my satisfaction, how did you define integral phi? Integral phi dm over r is equal to
summation I is equal to 1 to n alpha I measure of ei.
Yeah, summation I equal to 1 to n alpha I. This is just copying what we did for Riemann integral of a piecewise constant function, step functions. That is the width times height of that rectangle. Of EA. Here the length of that intervals will be replaced by quantification for EIs. Since EIs are sets in general, not intervals, the quantification is measure. So this is how we define. And let me also highlight why non-negativity assumption is made. Some of this EI could be of infinite measure. Therefore, if alpha i's can be negative, you may end up with forms infinity minus infinity. In order to avoid that, we took phi to be non-negative. Okay, so this is how we defined integral of a simple measurable non-negative function. Measurable, I don't have to say, non-negative simple function. And this is the ground level, level 0 or starting point. Okay, so now we know how to handle non-negative simple function. Starting with that, we would like to integrate more general functions. Okay, so that's what we are going to do today. But before that, let me also recall the following. If you see the definition of integral of non-negative simple function depends upon its canonical form. But we have seen through a theorem that even if phi is not in canonical form, we can write integral of phi. Okay, so that lemma, let me recall once again. Let B1, B2, etc. Bk be disjoint measurable sets and beta 1, beta 2, etc. beta k are B non-negative real numbers. Non-negative real numbers. Let us consider a function. Consider psi equal to summation beta I chi bi. I is equal to 1 to k. Psi is a simple function, but we don't know whether it is in canonical form. Because we don't know whether this beta 1, beta 2, etc. beta k are distinct. Okay. However, we have proved that integral over r phi dm will be equal to summation I is equal to 1 to k, the values taken beta I times measure of BA. So you can integrate a simple function which is not in canonical representation, but with the assumption that these beta 1, beta 2, etc. beta k are disjoint. So a slight improvement we did. Instead of working with canonical form, we can work with a slightly more general form. Is that okay?
Yes.
But still, we are in only integration of non-negative simple function. That's only we did so far. Okay. Now, as I told, our intention is to define integral for more general function, not just simple function. Of course, with simple function as our starting point. Okay. So to achieve that, we need the following proposition. Before that, one more comment or one more thing to recall. So far, we have integrated only over entire R, but we can integrate over some subset of R as well. Okay, so let E subset of R be measurable and phi be a simple non-negative function, non-negative simple function. I would like to have integral over E phi dm. There are variety of ways to do that. One is to think about a measure space based on E. Right now what we have is, we have R, we have a sigma algebra on R, and we have a measure on R, that sigma algebra. Instead of working on R, you work on E by taking its restriction. That is one way. To make this process more simple, what we can do is, instead of integrating phi, you can integrate characteristic function on E times phi on R. Action of phi on E and action of chi E phi on R would be same, because chi E gets switched on only on E. Are you with me?
Yes.
So instead of integrating over R only, we can integrate over any measurable subset. Okay. But again, only non-negative simple functions. So we defined simple function. We defined integral of a non-negative simple function when it is in canonical form. We have seen that we can also integrate a non-negative simple function when it is not in canonical form, but with some restriction that b1, b2, etc., bk are distinct. And we have also seen that we can define integral of a non-negative simple function over some subset of R. This is our progress so far. Okay. Now, if you want to extend the integral to more general function, one thing that we have to always verify is whatever you have done so far satisfies all the requirements that you expect for an integral. For instance, you expect that integral of a sum is equal to sum of the integral. That is linearity you expect. So that we have to prove in each stage. Okay. Now we have defined only for non-negative measurable function. So you have to prove that as far as non-negative simple functions are concerned, integration that you have defined is linear. Okay. So that's what we are going to do today in the beginning. Okay. So the following theorem. So our progress is, we have defined integration for a non-negative simple function. Using that, we want to go for more general function. But before that, you have to convince yourself that whatever integral you have defined satisfies property that we expect. So we are doing that. Let phi and psi be two non-negative simple functions. Of course, measurable functions. And CB a non-negative real. Then we have the following. As you expect, integral over R phi plus psi dm. Phi and psi both are non-negative simple. Therefore, phi plus psi would be a non-negative simple function, and you know how to integrate it. Is equal to integral over R phi dm plus integral over R psi dm. Of course, this is true for integral over E as well. Okay, and integral over R c times phi dm. We restricted c to be non-negative so that c phi will be again non-negative, and I know how to integrate it. Is equal to c times integral over R phi dm. Okay. In fact, integral phi plus psi dm, we don't bother over what? Over some e is equal to integral over e phi dm plus integral over e psi dm. And integral over e c phi dm is equal to c times integral over e phi dm. That's not a big thing. Once you have on R, you can have over e because of our definition. That integral over e is integral over R characteristic function times the function. So let us prove this. It looks trivial, but it needs a proof. Because right now I know how to integrate a simple non-negative function only when it is in canonical form, or at least in the form where that BI sets are distinct. Do you agree?
Yes, sir.
So we have to write it in that form first. Okay. Yeah. So how do I do that? 1 minute. So I'm going to write it in that form in which we can integrate phi. Let phi is equal to summation I is equal to 1 to, let us say, n alpha I chi ai, and psi is equal to summation j is equal to 1 to m, let us say beta j chi bj. Okay. B, the canonical representation. I would work with canonical representation of phi and psi, of phi and psi. My aim is to get a representation for phi plus psi. Okay, let Eij, I am defining new sets ai intersection bj. I varies from 1, 2, 3, etc. up to n, and j varies from 1, 2, 3, etc. up to m. So like this, I have defined mn sets. Note that union of ai, I is equal to 1 to n, you have to tell what this will be. I have commented on this in the last lecture. If alpha I chi ei is a canonical representation of phi, what can you say about AIs? Yes. One thing is that AIs will be disjoint. And second is that union of AI will give you the
Whole set.
R.
R. whole domain. Let us assume domain to be R. Okay. Similarly, union J is equal to 1 to M, Bj will be equal to R. Okay. Therefore, this we have commented in the last lecture. Once you have canonical representation, we have this. Therefore, AI, which I can write as AI intersection R, everything is happening inside R. That is equal to AI intersection Ri will replace by union Bj. J is equal to 1 to M. So that AI will be union J is equal to 1 to M AI intersection Bj. This is true for each I. Okay. And similarly, Bj would be Bj intersection R, which you can write as union I is equal to 1 to N AI intersection Bj for each J. Okay. J in 1, 2, 3, etc. up to M, and previous one for I in 1, 2, 3, etc. up to M. Okay. Therefore, the canonical representation that you have written for phi and psi can be rewritten as follows. Phi is equal to summation I is equal to 1 to N alpha I chi AI. This was the representation you started with. And this is equal to summation I is equal to 1 to N alpha I chi AI is this. Union J is equal to 1 to M AI intersection Bj. Do you agree that AI intersection Bj's are distinct? Or not distinct, sorry, disjoint? Are you people there? Do you agree that AI intersection Bj, those sets are disjoint?
Yes, sir.
Why?
AI and BJs are distinct.
AIs and BJs are disjoint. That's equal to. Therefore, this chi of A union B will be summation, which I have commented in the last lecture. That is alpha I times summation J is equal to 1 to M chi of AI intersection BJ. Okay. Chi of union is equal to sum, provided those sets are disjoint. So this is equal to summation I is equal to 1 to N, summation J is equal to 1 to M, alpha I chi AI intersection Bj. Okay. So this is your phi. Similarly, let us try to rewrite psi. Psi we took as summation J is equal to 1 to M beta J chi Bj. And that you can rewrite in a similar manner as summation I is equal to 1 to N. Replace Bj with this union. Okay. I don't want to write the details. You will get this. Beta J chi AI intersection Bj. So now you have representation for psi and chi. Therefore, phi plus psi. Therefore, phi plus psi. Now you can sum these two. Summation I is equal to 1 to N. Summation J is equal to 1 to M. Alpha I plus beta J times chi AI intersection Bj. Okay. And similarly, C times phi would be equal to summation I is equal to 1 to N, summation J is equal to 1 to M, C alpha I chi AI intersection Bj. So now you have representation for phi plus psi and C phi. Once you have a representation for a non-negative simple function, you can write its integral. provided either that representation should be canonical or the sets involved in that representation should be disjoint. Here I don't know whether this representation is canonical or not, but I know that AI intersection Bj are disjoint. Okay. Since AI intersection Bj, I is equal to 1, 2, 3, etc. up to n, j is equal to 1, 2, 3, etc. up to m, is a disjoint collection, the disjoint family of measurable sets we have. So now you can write the integral. Integral over R 5 plus psi, which is a simple measurable function, dm is equal to summation over I, summation over j, alpha I plus beta j, measure of AI intersection Bj. Do you agree?
Yes, sir.
How does it follow? It is not from canonical representation, from the lemma. In order to write integral of a non-negative simple function, it is not necessary that you need canonical representation. It is enough if the sets involved are disjoint. So we can use this. Now that is equal to summation over I, summation over j, alpha I, measure of AI intersection Bj, plus summation over I, summation over j, beta j, measure of AI intersection Bj. I split it into two summations. Okay. And in the first term, I would write summation over I, alpha I, summation over j, measure of AI intersection Bj, plus, and in the second, I would write summation over j, beta j, summation over I, measure of AI intersection Bj. Now I would request you to recall our representation for AI. AI I have represented as union of AI intersection Bj, and AI intersection Bj's are disjoint measurable sets. Therefore, measure of AI would be equal to sum of measure of AI intersection Bj by countable additivity.
Yes.
On measurable sets. Okay. Therefore, this is summation over I alpha I, summation j, measure of AA intersection Bj. I can write as measure of AA. So far, so good.
Yes. Yes, sir.
Yes.
Similarly, second sum will be summation over j, beta j. See the representation of Bj. Bj I have written as countable union of, in fact, finite union. Countable union of disjoint sets, measurable sets. Therefore, that will be measure of Bj. Okay. And if you see, the first one is actually integral over R phi dm. Because this one is canonical representation of phi. And similarly, the second one is psi dm. Okay. So, integral of sum is equal to sum of the integral, as we expected, is true if you have two non-negative simple functions. Okay. Similarly, I will not do the detail. Similarly, you can prove that integral over R c phi dm is equal to c times integral over R phi dm. So this establishes this proposition. It looks very innocent, but it is very important to see that at each stage of your integration process, the integral that you have defined satisfies the property that we expect. Okay. Now there is a corollary for this. Once you have for 2, you can have it for finite number. Okay. If phi 1, phi 2, etc. phi n are simple non-negative functions on R, then integral over R summation I is equal to 1 to n ai phi I dm is equal to summation I is equal to 1 to n integral over R phi I dm with an ai, obviously, where ai's are positive real numbers. So integral of linear combinations of non-negative simple function is equal to linear combination of the integral. Next corollary, again it is very simple consequent but worth to record. Let phi and psi be non-negative simple functions, measurable, obviously, simple functions such that phi is less than or equal to psi. Then integral over R phi dm. This is another property that we expect is less than or equal to integral over R psi d. Let us assume that all the functions are defined on whole R. Okay. So if phi is less than or equal to psi, then integral of phi would be less than or equal to integral of psi. Proof is simple. Okay. Write psi as phi plus a perturbation, namely psi minus phi. You know that phi is non-negative. You know that psi minus phi is non-negative because phi is less than or equal to psi. And psi minus phi is non-negative. So now it is like sum of two non-negative simple function. Therefore, by the property that you have proved, integral over R psi dm will be equal to integral over R phi dm for non-negative measurable simple functions. Sum of the integral and integral of the sum coincides. Integral over R psi minus phi dm. Each of them are non-negative. Now, have you done?
Yes.
Therefore,
Yes, sir.
because integral of psi is integral of phi plus some non-negative. Since integral over R psi minus phi dm is greater than or equal to 0. Why? Because psi minus phi is simple. Psi minus phi is greater than or equal to 0. Result follows. Okay. Now one more corollary, which is actually a nice corollary. So far we have integrated non-negative simple functions. And to write the integral, either we want our non-negative simple function to be in canonical form, or you want in a form where the sets involved are disjoint. Okay. Now let us see this corollary. Bear those points in mind and now see the corollary. Let B1, B2, etc. Bk be measurable sets measurable sets, and beta 1, beta 2, etc. beta k be non-negative real numbers. Then integral over R summation I is equal to 1 to k beta I chi bi dm is equal to summation I is equal to 1 to k beta I measure of bi. So this is the corollary. Before proving the corollary, you should understand why this corollary is important. What it tells, what it basically tells you. Look at the left hand side and look at the integrand. The integrand is a simple non-negative function. Yes or no?
Yes.
Integrand is a simple non-negative function. However,
Yes, sir.
that may not be in the canonical form. And that may not be in the form where the sets involved are disjoint. If you see B1, B2, etc., Bk disjoint is not given. But still, its integral can be easily written. It will be equal to the values taken, beta I, multiplied with quantification of each set. So first we defined integral of a non-negative symbol function when it is in canonical form. Then we slightly improved. We don't want canonical form. Only thing what we want is sets involved are disjoint. Now we are saying even disjointness is not needed. Are you with me?
Yes, sir.
That is disjointness of BIs are is not needed. Not needed to define integral. So now we have improved a way lot from canonical form to any form in which beta 1, beta 2, beta k need not be distinct. Beta 1, beta 2, etc. beta k need not be distinct. B1, B2, B3, etc. bk need not be disjoint. Okay. Proof. Now let us see the proof of the corollary. It is quite easy. Consider phi I is equal to beta I chi bi. Okay. Then each phi I is a simple measurable function. Then each phi I is simple. Measurable, I don't have to say. Now apply the previous corollary. Integral over R summation phi I dm is equal to summation over I integral over R phi I dm. Okay. And that is equal to summation over I beta I measure of BA. Okay. Try to do that. Okay. I don't have to spend more time on it. Even if you have some issues, please take your own time and try to prove this corollary. Okay. But I wanted to write this corollary on record because it is important point that we don't want our simple function to be in canonical form. It can be in more general form. Okay. So what we have is that given a non-negative simple function, I know how to integrate it. That's what we know so far. Okay. With that as 0th level or the starting point, we want to define integral of more general function. And we are going for the first step towards it. Okay. So we shall deal with more general functions, not just non-negative simple function. Now, what is the more general function we are targeting right now is the following. Let f be a bounded real valued function on a measurable set E with measure of E to be finite. So we are in a slightly more general case, but still there are some assumptions like the function should be bounded. I don't want non-negativeness, but the function should be bounded. It should be defined on a measurable set E whose measure is finite. So I don't deal with functions that are defined on entire R, for instance. I cannot deal. I can deal only with functions which are defined on sets whose measure is finite. Okay. Please recall the Riemann integration. There you dealt with bounded function. Here also you have bounded functions. Okay. There you dealt with finite intervals of the type AB. Length is finite. Here instead of intervals, you have sets. Instead of saying that length is finite, we have measure is finite. So we are again in almost in the same situation as Riemann. Now remember what Riemann did. Riemann defined the lower Riemann integral and upper Riemann integral. And how did he define lower Riemann integral? Can somebody remind me? What is lower Riemann integral? Lower integral.
By taking the infimums each interval.
Okay. Taking the infimum. So I will draw the picture instead of writing too much. So you have a function like this. You have an interval AB. You have divided into several subintervals. And in each subinterval, let us say xk minus 1 xk, you approximate this function by a constant. That constant you take as infimum. Okay, infimum.
Yes, sir.
And now do it for each. And that will give you only upper sum or lower sum. And then to go for upper
Then
integral or lower integral, what you do?
we have to do it for arbitrary partitions.
And then make this either take supremum or take infimum, right? Overestimate and make the overestimate better and better, or underestimate and make the underestimate better and better. Same thing we are going to do. Okay, for that only I ask you this. So now I am going to define. So let me write analogous to Riemann integral. Let us define. One more thing before writing, I would ask you, instead of saying that you take infimum and supremum and so on, what you can keep in mind is that we are approximating the given function by step function. Right? One step functions below the given function, and in one step functions above the given functions. Do you agree?
Yes,
Yes.
sir.
So you are approximating the given function by step functions which is less than the given function and step functions which are greater than the given function. Keep that in mind. Okay. Now I am going to define lower integral of f dm, but Lebesgue integral. So in order to understand Lebesgue, I am writing dm. Okay, and I will put similar to Riemann. I will put a bar in the lower. So this is lower Lebesgue integral. How do I define? Is equal to, instead of integrating the given function, there you integrate the step function. Here I will integrate the
simple function.
Simple function phi dm. Okay. For what phi? Phi less than or equal to f. For phi is less than or equal to f. I am estimating from below, and you have to make this estimate better and better. So take supremum, where phi is simple. So lower Lebesgue integral is defined as, instead of integrating f, you integrate simple functions which are less than f. That you know how to integrate. I will come to that later. And then you take supremum. Okay. Similarly, if you want Lebesgue, upper Lebesgue integral f dm, what you do is, instead of integrating f, you integrate step function psi dm, where psi is something greater than or equal to f. That is why we are calling it upper. Okay, so we are overestimating the given integral, and to make this overestimate better and better, take infimum over all simple function. Psi is simple. Is that clear?
Yes.
Do you
Yes,
see
sir.
that it is exactly what we have done in Riemann integration?
Yes.
Instead of simple, you took the step functions with the steps as infimum and supremum, small mk and capital mk. Okay, but if you see right hand side, you may have a small issue, because do you know how to integrate a simple function? Right hand side demands integrating a simple function. Do you know how to integrate a simple function?
Sir, we know only for non-negative.
Only for non-negative, but here I did not assume non-negativeness. Why we assumed non-negative? What was the issue if it is negative? I told you.
Minus infinity form.
Infinity minus infinity. If you have summation alpha I chi ai, and some of the ai's are of infinite measure, then you will end up with infinity minus infinity issue. But here that will not come. That will not arise. Why?
We have
Measure.
taken finite
Measure
measure.
is less than
Finite measure only. So we don't bother whether the symbol functions are negative or non-negative. We don't really bother. Are you with me? Only reason to introduce non-negativity is that we wanted to avoid infinity minus infinity, because measure of some sets ai can be infinity. Here it will not happen, because we already are integrating over only e, and measure of e is finite. Okay, so whatever is appearing on the right hand side, namely integral of simple function, which is not non-negative, which may not be non-negative, we know how to perform. Is that okay?
Yes.
Now, again, I will ask you to recall Riemann integration. So you have defined upper Riemann integral and lower Riemann integral. Now, what did you do there? So one is like approximating from inside, and other is like approximating from outside. Which approximation you should take is a question. Okay? Whether you should underestimate and make the underestimate better, or you have to overestimate and make the overestimate better is a question. How Riemann tackled that question?
Both are
If
equal,
both
then
are equal, then
No, not both are equal. He did not bother about whether to take underestimate or overestimate. He considered only those functions for which underestimate becomes equal to overestimates. Okay, that class of functions only he considered. Okay, and he called that function is Riemann integrable if upper Riemann integral is equal to lower Riemann integral. So what will be the next step here that you feel?
Lebesgue consider only those functions for which
Or you can make a definition. We can call a function to be Lebesgue integrable if upper Lebesgue integral coincides with lower Lebesgue integral. Okay. We say that f is Lebesgue integrable. F is Lebesgue integrable if and only if integral over E f dm lower Lebesgue is equal to integral over E upper f dm. Okay. And after defining Riemann integral, like upper Riemann integral is equal to lower Riemann integral, we searched for what classes of functions are Riemann integrable. For instance, you might have seen that every continuous function is Riemann integrable. If a function is monotonic, then it is Riemann integrable. If a function has finite number of discontinuity or a countable number of discontinuity, then it is Riemann integrable and so on. So we want to know what classes of function upper Riemann integral will be coinciding with lower Riemann integral. Yes or no? So what you want to do here?
Here also we find
Same question we want to see. What classes of function you will get upper Lebesgue integral is equal to lower Lebesgue integral. However, in comparison with Riemann, here Lebesgue integral behaves more nicely. You can have a necessary and sufficient condition for Lebesgue integrability. Okay, there you only know that a continuous function is Riemann integrable. You cannot say a function is Riemann integrable if and only if it is continuous. A function is Riemann integrable if and only if it is monotonic. Such results you cannot say. You have a series of sufficient condition. Here I have a nice necessary and sufficient condition. Okay, so that is next theorem. Let f be, but remember we have achieved integration only for functions that are bounded and domain is measurable and it is of finite measure. Let f be defined and bounded on a measurable set E with measure of E finite. So I will underline or I highlight these two. Function is bounded and the set is measurable with the finite measure. Then the theorem says the following. Then f is Lebesgue integrable, meaning upper Lebesgue integral coincides with lower Lebesgue integral. Meaning whether you are underestimating with step function or you are overestimate by integrating a step function, not step function, simple functions, the answer is immaterial. That will happen if and only if f is measurable. See, the nice condition. Measurability of the function is enough to guarantee that it is Lebesgue integrable. Thus, the measurability happens to be the right assumption to start the Lebesgue integration theory. That's why we started with measurable functions. Proof is not that trivial. It is bit involved. But before that, let me again tell you, we have achieved Lebesgue integration only for bounded function. Can be negative or positive, doesn't matter, but it is bounded function. And also integral is to be defined, function is to be defined on measurable set with a finite measure. So from non-negative simple function, we lifted it to bounded functions defined on finite measurable sets, finite measure sets. Anyway, now let us go to the proof of this. As I told you, it is a bit involved. It is not that trivial. So it is a necessary and sufficient condition. Let me start with the fact that f is measurable and prove that it is Lebesgue integrable. Okay. And blanket assumption is that it is a bounded function defined on a measurable set with a finite measure. Let f be a bounded function, bounded measurable function. So I am assuming measurability. Defined on a set E with measure of E finite. We have to prove that f is Lebesgue integrable. For that, we have to prove that the upper Lebesgue integral coincides with the lower Lebesgue integral. Okay. First of all, we know that the function is assumed to be bounded. Okay. Let modulus of f of x is less than or equal to m for all x in E because of boundedness. Such an m exists. Okay. So roughly the graph will be something like this. Okay. Fx will lie between minus m and m. What I am going to do is I am going to subdivide the y-axis. Looking at minus m range, I am going to subdivide it with equal partition. Step size is equal. Choose a mesh step. I mean partition size m by n, and consider. So what I am going to do is this is 0, m by n, 2m by n, and so on. This will be nm by n. Okay, and negative also you have, that is minus m by n, minus 2m by n, and so on. Okay. So each step size is m by n. And consider Ek is equal to set of all x in E. I am going to divide the domain by partitioning the range. Or in other words, taking inverse image. This is one difference I told between Riemann and Lebesgue. You don't divide the domain, you divide the range and then look into the inverse image. Ek is equal to collection of all x such that k minus 1 m by n less than fx less than or equal to km by n. With minus n less than or equal to k less than or equal to n. For the time being, n is fixed. You divide minus m into equal subintervals, minus m into equal subinterval of size m by n, and then you take the inverse image and consider Ek. Okay. Now you have to observe certain things from Ek, certain facts about Ek. First, do you see that Ek's are disjoint? Look at Ek. There is nothing to think too much. Look at Ek. Ek consists of all x in the domain, namely E, such that fx lies between k minus 1 m by n and km by n. And Ek plus 1 We'll consider fx between suitable numbers. Like that, you have from e minus n to en, e minus n minus 1, and so on up to en, e naught, e1, e2, etc. en. Okay. Do you see that these are all disjoint?
Yes, sir.
Yes.
That's why I did not pick. If you see the definition, I did not write less than or equal to both sides. One side I have put strictly less than. Okay. Note that then 1. EKs are disjoint. Okay, that is one observation. Now, second observation about EK. Can you say that EKs will be measurable? What is F?
Yes, sir. As
Boundary
f is measurable.
F is measurable. Okay. What do you mean by a function is measurable? Collection of all x such that fx less than alpha, fx greater than alpha, fx less than or equal to alpha, fx greater than or equal to alpha, etc. are measurable for any real number alpha. Yes or no?
Yes, sir.
Yes.
Yes, sir.
Use that. Use that. Okay. Then EKs are measurable. I will not write the details. EKs are measurable. Because f is measurable, and then apply the definition of measurability of function. Okay. And finally, E will be equal to union EK. K is equal to minus n to n. Is that clear?
Yes, sir.
Because for all x in E, fx lies between minus m and m. And that will be covered by EKs when k runs from minus n to n. Okay. So these are some trivial observation about EK. Now,
माइनस एन ड्रॉ करके देखिए, ये रेंज में नहीं आ रहा है. E
now let
माइनस
us.
एन, सर एक्चुअली E माइनस एन को ड्रॉ करके.
If you have something to say, you say. I don't know whether you are talking there or to me.
So
Yes.
Actually E minus n not belongs to range. Please draw it and see.
Why is it so? E minus n.
So because minus n minus 1 by m by n, तो वो actually minus m से शिफ्ट हो जाएगा नीचे, और नीचे आ जाएगा. That's
I
why.
am considering only those x in E for which fx lies between these two. So why are you saying E?
सर जो क्वांटिटी जो बन रहा है ना, माइनस m minus 1 m times divide by m, it is strictly less than minus m. That's
I
why.
don't understand your point. Please think over this 1 minute. You have minus m to m. Okay. And you have here, this is minus n m by n. And here you have n m by n. In between you have 0. This you have m by n and so on. This is n minus 1 m by n. Okay. And I don't, you are saying something about this minus n minus 1. Minus n.
Yes, sir.
So this will be minus m by n. And this will be minus 2m by n and so on. Do you want to say that it will be minus n plus 1, not minus 1?
Yes, sir.
That's what you wanted to say?
Yes, sir.
That's okay. That's okay. So this will be minus n m by n. That's okay. So the next one you wanted to say, this will not be minus n minus 1. That's what you want to say.
Yes, sir.
Too much of disturbance. But whether that will affect saying that E will be is equal to union EK.
No, sir.
That's what I want. Okay. I did not write here minus n minus 1 m. If at all I have told that you can avoid, but that will not affect the fact that E's will be equal to union Ek. It's very disturbing. Your voice is not very clear. Okay. Yeah. So there is no harm in writing Ek like this. And these are the observation which is going to be crucial for us. Ek's are disjoint, they are measurable, and union of Ek will give me E. Now, let us consider the simple functions. I think we forgot what is our main aim. So let me remind you, the target is to prove that f is Lebesgue integrable. For that, we have to prove that upper Lebesgue integral is equal to lower Lebesgue integral. So for that, I am going to consider the simple function because we know to integrate only via simple functions. Consider the simple functions. Psi nx is equal to summation k equal to minus n to n km by n chi ek of x and phi n of x equal to summation k equal to minus n to n k minus 1 m by n. Roughly, you can think like you are taking supremum and infimum in each of those intervals, subintervals, and then you are approximating by simple functions, one from above and one from below, roughly. Okay. So with this definition of psi n and phi n, what you can observe is the following. Again, I don't want to write the detail so that phi nx will be less than or equal to f of x will be less than or equal to psi nx for every x in E. That will follow from the definition of Ek. Ek you have defined as those x for which fx lies between k minus 1 m by n and km by n. Okay. With that and with the definition of psi n and phi n, try to see whether you can write phi nx less than or equal to fx less than or equal to psi nx. I will just put a question here. How? You have to convince yourselves. Okay. Now, what we are interested is the Lebesgue integral, upper and lower. Okay. Now, infimum of integral psi x dx, where psi is greater than or equal to f, psi symbol. This is what we want to find for which integral? Upper integral, upper Lebesgue integral. Okay. So if you want upper Lebesgue integral, you have to take infimum over collection of all symbol function greater than or equal to f. Psi n only forms a subcollection of symbol function greater than or equal to f. So do you see that this will be infimum over this will be less than or equal to integral over E psi nx dx? Do you see this?
Yes, sir.
How does it follow? This is infimum over large set, whereas this psi n is just one element in that collection. Because psi n is greater than or equal to f of x and psi n is simple. Therefore, psi n's are only some elements in this collection and you are taking infimum over the entire. So infimum over the entire collection will be less than or equal to integral over each element in that collection. Okay. So, and now since psi n's are simple, non-negative is not needed because the sets involved are finite measure. So I can write integral of psi n. Now can you tell me what will be integral of psi n? It will be equal to the values taken, which is km by n, in the measure of this set Ek. Summation k is equal to minus n to n mk by n measure of Ek. Okay. Now let us compute this was upper Lebesgue integral. Now let us compute the lower Lebesgue integral. Integral over E phi x dx. Instead of dx, I think it is better to use dm. dm phi x dm, or phi dm is also okay. But once you don't have confusion whether it is Lebesgue or Riemann, you can even write phi of x dx, doesn't matter. Then take supremum. Supremum phi less than or equal to f, phi simple. This is actually the lower Lebesgue integral. Okay, and this will be less than or equal to integral over e phi n dm.
So greater than equal to.
Greater than or
Sir,
equal.
great.
1 minute, 1 minute. Yes, yes, yes. If I was concentrating on this. Yeah, just for uniformity. But even if I am right dx, you should understand from the context whether I mean Riemann integral or Lebesgue integral. Okay, and this will be greater than or equal. Because phi n's are only some elements in that collections. Phi n's are simple and phi n's are less than or equal to f. Okay. Since phi n's are simple, you know how to integrate it. This is equal to summation k is equal to minus n to n. Values are k minus 1 m by n, and measure of the sets involved, measure of ek. Okay. Now, let us see the difference. Therefore, 0 less than or equal to infimum over psi of x dx, psi dm minus supremum over phi dm, supremum over all simple functions greater than, less than, etc. Okay, this will be 0 less than or equal to is clear. One is infimum and one is supremum. So this will be less than or equal to the difference of these two. Because infimum is less than or equal to this and supremum is greater than or equal to this. Apply that, you will get this is less than or equal to m by n summation k equal to minus n to n measure of ek. From how? From what? This follows from star 1 and star 2. And this is star 1 and this is star 2. That two inequality will give this. 0 less than or equal to is very clear. Okay. Is that okay?
Yes.
And what is EKs? Measurable. And what is union of EKs is E, and EKs are disjoint. Therefore, again use the countable additivity for measurable set. Summation of measure of EK will be measure of E. So this will be equal to m by n measure of E. N we have fixed at the beginning, k was changing. Now you can do it for any n. Okay, you can partition into different subintervals. I mean, first there was, say, for instance, k number of subinterval, then you can keep on increasing the number. Okay. So this n you can change. So from that, what you get, since n is arbitrary, apply sandwich theorem. Since n is arbitrary, we have left hand side is anyway 0, right hand side is fixed, capital M is fixed, measure of E is fixed, but n is varying. You can make n tending to infinity. Since n is arbitrary, we have infimum integral over E psi dm minus supremum integral over E phi dm is 0. Okay, this infimum, when I say psi greater than or equal to f, psi simple. And this supremum, when I say phi less than or equal to f, phi simple. Okay, what does it mean? The upper Lebesgue integral minus lower Lebesgue integral, or whatever it is 0. Okay, and that implies upper Lebesgue integral f dm is equal to lower Lebesgue integral f dm, or vice versa. That implies f is Lebesgue integrable. At least I should finish this theorem now. So, assuming that f is bounded and measurable, we could prove that f is Lebesgue measurable. Now, conversely, suppose f is Lebesgue measurable. I have to prove that Lebesgue integrable. We have to prove that f is measurable. That is integral over E f dm lower is equal to integral over E f dm upper. Somehow I have to prove that f is measurable. What I am going to prove is that f is equal to something almost everywhere, and that something is measurable. We have proved a result. If f is equal to g almost everywhere and g is measurable, then f will be measurable. Okay. To prove that f is measurable, what I will do, I will prove that f is almost everywhere equal to a measurable function. Okay. Now I have to construct that measurable function which is equal to f almost everywhere. For that, let us start with what we have in hand. What we have in hand is the lower Lebesgue integral is equal to upper Lebesgue integral. By definition, upper Lebesgue integral f dm is infimum of integral of psi dm, psi greater than or equal to f, psi simple. This is the definition of upper Lebesgue integral. And lower Lebesgue integral definition is supremum phi greater than or equal to f, phi simple integral phi dm. Is that okay?
Phi less than equal to x.
Phi less than or equal to. Thank you. Phi less than or equal to. One is underestimate and one is overestimate, and then making this underestimate and overestimate better and better. Okay. Now what I am going to do is to apply the infimum and supremum definition. Infimum is greatest lower bound and supremum is least upper bound. Okay. So if you have supremum, nothing less than it can be an upper bound. And if you have infimum, nothing greater than it can be a lower bound. Okay. So that I am going to apply. Then by the definition of infimum, for each n in n, there exists a simple function psi n greater than or equal to f, such that integral over E psi n dm is less than integral over E f dm upper plus 1 by 2n. Upper is infimum, so nothing greater than infimum can be a lower bound. That's what I applied. Similarly, there exists a simple function phi n less than or equal to f, such that lower Riemann integral, not Riemann, Lebesgue integral f dm minus 1 by 2n is strictly less than integral over E phi n dm. Because this is supremum, nothing less than it can be an upper bound. Is that okay? That is, lower f dm is less than integral over E phi n dm plus 1 by 2n. Okay. This can be put as star 3 and this is star 4. Just I applied the definition of infimum and supremum. Okay. Therefore, now I am going to analyze star 3 and star 4. integral over E psi n dm minus 1 by 2n from star 3 is less than integral over E f dm upper. But we know that this is equal to lower because we know that f is Lebesgue integrable. So upper Lebesgue equal to lower Lebesgue. And lower Lebesgue from star 4 is less than integral over E phi n dm plus 1 by 2n. So we got integral over E psi n dm minus 1 by 2n is less than integral over E phi n dm plus 1 by 2n. That is integral over E psi n dm minus integral over E phi n dm, because this cannot be infinity and all, you can transpose to the other side, is less than 1 by n. Okay. So this is a crucial estimate that we may use later. So this is star 5. Okay. Now our aim is to get a function which is measurable and which is equal to f almost everywhere. Now define psi star is equal to lim inf psi nx and phi star is equal to lim sup phi n. I don't have to write x. Or psi star of x equal to lim inf psi n of x and so on. So I have defined two new functions. Okay. Now do you see that phi star and psi star will be measurable?
Yes, sir.
Because psi n and phi n are measurable. Then psi star and phi star are measurable. Okay. Further, use this fact. Okay. You will also get that phi star is less than or equal to f is less than or equal to psi star. Because of the construction of phi n and psi n, phi n's are greater than f and psi n's are less than f. Am I right? Yes, phi n's are greater than f and psi n's are less than f. With that, okay, you have this, which I will put as maybe star 6. Now what I am going to do is that this f will be coinciding with phi star or psi star almost everywhere. Already you know that phi star and psi star are measurable, so that you will get f is measurable. Now to prove that f will coincide with phi star or psi star almost everywhere. Almost everywhere means where it doesn't coincide should be of measure 0. Okay. So let me consider A equal to collection of all x in E consider such that phi star of x is strictly less than psi star of x. Inequality we have, look at star 6, keep that in mind and let us consider those points where which phi star x is strictly less than psi star x. That I can write as union of set of all x in E such that phi star of x is less than psi star of x minus 1 by k. Usual technique. I want to write it as countable union. K is equal to 1 to infinity. And each of this set I will define as AK. This is equal to AK union K equal to 1 to infinity. Okay. Now, for each fixed k, each k in n, you can take n large enough. For large enough n, remember phi star and psi star are lim inf and lim sup. Okay, with that in hand, for large enough n, we have phi nx is less than psi nx minus 1 by k on ak. What is AK? AK is defined as collection of all x in E such that phi star x is less than psi star x minus 1 by k. So on AK, what I know is phi star x is less than psi star x minus 1 by k. But phi star is in terms of lim sup and psi star is in terms of lim inf. So for large enough n, apply the definition of lim inf and lim sup. I can say that phi nx is less than psi nx minus 1 by k. Again, this needs to be convinced. Okay. I have already given you a hint. Apply the definition of lim sup and lim inf. You will get it. And on AK, I know that phi star x is less than psi star x minus 1 by k. From that, you have to pass to phi nx less than psi nx minus 1 by k for large enough n. And thus, phi nx minus, not sorry, psi nx minus phi nx will be greater than 0. It will be greater than 1 by k, so it will be greater than 0 in particular. Therefore, integral over E psi n dm minus integral over E phi n dm is equal to integral over E psi n minus phi n dm. That is greater than or equal to integral over AK. This you need to prove. Psi n minus phi n dm. I think I have not listed this property. If you have a simple measurable function, integral over larger set, integral over E will be greater than or equal to integral over E dash if E is a superset of E dash. Okay, f dm. This you have to prove. Not for all function, but for the symbol functions. For f symbol. I will not use f, I will use something else, phi. This you try to prove. Again, expected. Integral over larger set will be greater than or equal to integral over smaller set. But for simple measurable function. And this is equal to phi n minus psi n is greater than 0. So this will be equal to measure of AK by k. Because phi n minus psi n is greater than or equal to 1 by k on AK for large enough k. Okay. Thus we have large enough n. 1 by k measure of AK. I will be little bit quick here. Is integral over E phi n psi n dm minus integral over E phi n dm. Okay. And this is less than 1 by n by star phi, which is less than 1 by n. This is from star phi and this will be star 7, I think, and star 7. Okay. Now let n tending to infinity. Letting n tending to infinity, we have measure of AK is equal to 0 for all k. And therefore, measure of A would be equal to 0. And therefore, measure of A is equal to 0. Spend some time on this. I know that I have put so many gaps, but you have to fill it. So since measure of AK is 0 and A is equal to union AK, measure of A will be 0. And what is A? A is collection of all x in E such that phi star of x is strictly less than psi star of x. That is of 0 measure. Thus, and now remember this star 6. F is always between phi star and psi star, and set on which phi star is strictly less than psi star is of measure 0. That means equality holds for almost all x. Therefore, from star 6, from star 6, we have f equal to phi star, and that will be equal to psi star almost everywhere on E. Where that equality doesn't hold is of measure 0. Okay, and you already know that phi star and psi star are measurable, therefore f is measurable. Since phi star is measurable, I will stop with this. F is measurable. So what is our progress so far? We have defined integral of a non-negative simple function. First stage, that is this, not first stage, that is the ground level, 0th stage. And the next stage, I took f to be a bounded measurable function, and I have defined upper Lebesgue integral and lower Lebesgue integral, and we proved that both will coincide whenever f is measurable. So, motivated by this proposition, this finishes the proposition. Motivated by this, I make a definition and stop. By the above proposition, we have the following definition. Let f be a measurable function defined on a measurable set E with a finite measure, with measure of E less than infinity. Measurable bounded function maybe. And then we define measurable bounded function. The Lebesgue integral of f. I want to complete this definition because this will be our starting point of the next lecture, over E by integral over E f dm. Either you can overestimate and make the overestimate better and better, or underestimate and make the underestimate better and better. Both are equal. We already proved because of the measurability condition. But what the definition is, infimum of integral over E psi dm, where psi is greater than or equal to f, psi simple. So this is going to be the definition of the integral. Okay, I will stop with this. So we started with a non-negative simple function, and we went up to the integral of a measurable bounded function on a measurable set with a finite measure. Okay. Next step, we will avoid this assumption finite measure, and we can define it for any function, any bounded measurable function over any set. And again, we will avoid boundedness also. And finally, we will talk about integral over any set and any function. Okay, that's our aim. Okay, so let me stop with this. Thank you.